All right, so this is Algebra Lesson 8, and someone asked about problem number 6 in homework 3. So let's take a look at the problem. We have the permutation sigma equal to 1, 2, 3, 4, 5, 6. In S6, and we want to compute sigma squared and sigma cubed. That's the first part. So if you were to write, so this sigma is a 6 cycle. If you were to write sigma in the standard form, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 6, and 6 goes back to 1. So sigma squared, that means sigma composed with sigma. So 1, 2, 3, 4, 5, 6. Let me just write it in standard form. Sigma sends 1 to 2, and then sigma sends 2 to 3, so 1 ends up at 3. Sigma sends 2 to 3, and then again sigma sends 3 to 4, so 2 ends up at 4. Sigma sends 3 to 5, sorry, 3 to 4, and then 4 to 5. 4 goes to 5 goes to 6. 5 goes to 6 goes to 1. 6 goes to 1 goes to 2. So sigma squared is this permutation in standard form. Any questions about this? So this is the standard form. And suppose we want to write it in cycle form. So 1 goes to 3, 3 goes to 5, 5 goes back to 1. That's a 3 cycle. Let's see, 2 hasn't been used here. 2 goes to 4, 4 goes to 6, 6 goes back to 2. So sigma squared is this permutation, which is a product of 2 disjoint 3 cycles. Right? So sigma squared is a product of 2 disjoint 3 cycles. What about sigma cubed? So in standard form, if you apply sigma 3 times, 1 goes to 2, 2 to 3, 3 to 4. 1 ends up at 4. 2 goes to 3, goes to 4, goes to 5. 3 goes to 4 to 5 to 6. 4 goes to 5 to 6 to 1. 5 goes to 6 to 1 to 2. 6 goes to 1 to 2 to 3. So this is the standard form. And if you write this in cycle form, 1 goes to 4, and 4 goes back to 1. 2 goes to 5, 5 goes back to 2. 3 goes to 6, 6 goes back to 3. So sigma cubed is a product of 3 disjoint 2 cycles. And a 2 cycle is just another word for a 2 cycle is a transposition. But sigma cubed is a product of 3 disjoint 2 cycles. And Any questions about that? Okay, that was part A. Now notice also that we started with a permutation sigma in S6, a 6 cycle. And 6 is 2 times 3, and it's also 3 times 2. So we see that sigma squared is a product of 2 3 cycles, and sigma cubed is a product of 3 2 cycles. And part B is to show the following. Let me just use the same notation as I do here. So suppose n is k times d, and let sigma be an n cycle. In Sn, we want to show that the dth power of sigma is a product of d disjoint k cycles. So suppose that sigma is just the k cycle. 1 goes to 2, 2 goes to 3, 3 goes to 4.
Can't really see the top part. Thank you.
That's just the statement of the problem. Okay. So let's see. So in general, let's see, like sigma to the d of 1. So what happens if you apply sigma d times? 1 goes to 2, 2 goes to 3, 3 goes to 4. So if you iterate the permutation sigma d times, every time you apply sigma to a number k, number n, number r, it goes up by 1 until it gets to n, and then it comes back to 1. So sigma to the d of 1 is d plus 1. Sigma to the d of 2 is d plus 2, and so on. What happens if you look at, so sigma to the d will look like this: 1, 2, 3, d plus 1, or I should say, so 1 goes to 1 plus d, 2 goes to 2 plus d, 3 goes to 3 plus d, 4 goes to 4 plus d, n goes to n plus d, with the understanding that n plus n goes to 1, right? So when you get to n, it comes around. So when you apply sigma to n, you get 1. When you apply sigma twice to n, you go to 1 to 2, and so forth. So this is all what we might say modulo n. It's sort of, it comes around. And so let's look at the orbit of, let's sort of compute the cycle of sigma to the d starting with 1. You have 1 goes to d plus 1. You add d each time. It goes to d plus 2, goes to 2d plus 1, goes to 3d plus 1. Eventually, you get to k minus 1d plus 1, right? Because this is after k minus 1 iterations. K minus 1d plus 1, this is the same as KD minus d plus 1. KD is equal to n. This is n minus d plus 1. The next iteration goes to n plus 1, which is 1. So the cycle generated by 1 is 1d plus 1, 2d plus 1, up to k minus 1d plus 1, and then it comes back to 1. And this is a cycle of how many numbers? 1 plus k minus 1. This is a k cycle. So if you trace out what happens when you apply sigma to d to 1, you get this k cycle. And if you do the same thing to 2, you get 2d plus 2, 2d plus 2, up to k minus 1 d plus 2. And then it comes around, when you add d, it comes around to 2. So you get another k cycle. And if you want to understand what's going on, you actually should do this with a number of explicit examples. And what you will see is that sigma to the d, you have a product of cycles. 1, d plus 1, up to k minus 1d plus 1. And then it comes around, times 2 times d plus 2. Next would be 2d plus 2, up to k minus 1d plus 2, and then it comes around. And you have this for all the numbers from 1 up to d. D, 2d, 3d, up to kd, and then it comes around. And what we have here are d disjoint k cycles. But really, the best way to understand this is to do a number of examples. So part 1 is an example of this general fact, and you should do other examples. For example, suppose we let sigma suppose you take a 10 cycle in S10 and compute. So 10 is 2 times 5. So compute sigma sigma squared. And also compute sigma to the 5th. And you'll see that sigma squared is a product of 2 5 cycles, and sigma to the 5th is a product of 5 2 cycles. This will be the cycle 1 3 5 7 9 times the cycle 2 4 6 8 10. This will be the product of 5 2 cycles. Oops. Yeah. So once you calculate a number of examples, then you understand exactly what the question is asking you to prove. So, when you get to a more or less advanced math class, then the problems don't take a long time to write down, to state the problem, but it can take an hour or two of thinking to understand what's going on, to be able to compute examples and calculate, in this case, permutations, and then understand from the examples what's really happening and prove the general statement, prove the general theorem. Any questions about this?
Professor, can you do the number 7?
On the same homework?
Yeah, 7.
Okay. So so homework 3, number 7, we have a case cycle in Sn. And we want to prove that if you iterated k times, you get the identity, and k is the smallest integer, positive integer, such that when you iterate or multiply sigma by itself I times, you get the identity. So sigma is some k cycle, A1, A2, up to A sub k in Sn. And so this is a k cycle. And we want to prove that sigma to the k is the identity, and k is the smallest integer I, such that sigma to the I is the identity. So statement A, well, again, I mean, one way to draw a picture of a k cycle is you have A1 goes to A2, goes to A3, going around, goes to A sub k minus 1, goes to A sub k, goes back to A. All right, every time you apply sigma, it sends each number to the next one in this circle. So you go once, twice, 3 times. When you go k minus 1 time, when you go k times, you're back where you started. I mean, that's, you know. So sigma of A1 is A2. Sigma squared of A1 is A3. Sigma cubed of A1 is A4. Sigma to the k minus A1 is A sub k. And sigma to the k of A1, that means sigma of AK, that's back to A1. And the same works with every other element in this cycle. So you have sigma of AI, sigma of AJ. Suppose you take any j between 1 and k. Sigma of AJ is AJ plus 1. Sigma squared of AJ is AJ plus 2, at least until you get, let's see, sigma to the k minus jth power, right, of AJ is equal to AK. Right? Because you do this k minus j times, so you go AJ to AJ plus 1, AJ plus 2, AJ to k minus j, that's k. So sigma to the k minus j plus 1, that brings you back to A1, and sigma to the k is going to be A sub j. You apply this j minus 1 more times. So that is a proof. You know, you have to make sure you write it down with all the detail that's necessary, and I'm not doing everything here, but enough so you understand exactly what's happening. This is a proof that sigma to the k is the identity. And if I is less than k, if I is a positive integer and equal to or less than k minus 1, well, then right away you can see that sigma to the I of 1, of A1, is A sub I plus 1. And I plus 1 is less than or equal to k. If I is less than or equal to k minus 1, I plus 1 is less than or equal to k. So this is not A1. Implies sigma to the I is not equal to the identity permutation. So the words that I'm saying need to be written down when you're writing out the proof on a piece of paper. But this is exactly what's going on. If I is less than k and you apply sigma to the I to the A1, you go I steps around the circle. You don't go far enough to come back where you started, so you don't have the identity. But if you go exactly k steps, then you always come back to where you started. Okay. Questions about this? So someone asked me to do the rest of the problems, so let me just point out how to do some of them quickly. So 9 actually is maybe too simple. We have the multiplicative group of non-zero rational numbers. And in this, we have subgroups, the set of all powers of 2. So that's the positive powers and the negative powers, which are the fractions. And you also have the subgroup of the powers of 3. So you have 3 to the 0, which is 1, 3, 9, 27, 1/3, 1/9, and so forth. And the only thing that's in both of these groups is the identity. So the intersection of 2 to the k with the subgroup 3 to the k is just the identity element 1. Any questions about that? For number 8, you can write a sigma in Sn is a product of disjoint cycles. That's a theorem we proved about every permutation having a unique representation as a product of disjoint cycles. So if each cycle is a transposition, which means a 2 cycle, that means sigma is of the form A1, B1, A2, B2, let's say AK, B sub K. It's a product of K transpositions. So sigma squared, when you multiply this with itself, so here's sigma, Here's sigma. But disjoint cycles commute. So I can rearrange the cycles as A1B1 times A1B1 and A2B2 times A2B2 and so forth up to AKBK times AKBK. But you multiply a transposition by itself, you get the identity. And the product of the identity is the identity. So if your permutation is a product of transpositions, then it has order 2. That means order 2 means that 2's the, if you take sigma to the power 2, you get the identity. And if sigma is a product of k cycles, but not of order 2, so you have, say, A1 up to A sub, I don't know, M up to AM, and then some other stuff, other cycles. If you take sigma squared, it's the product of all these different cycles squared, and this is not the identity. It's only the identity, because we proved in the previous problem that the smallest power of sigma, if you have a k cycle, in this case, call this k, if you have a k cycle, the smallest power of sigma, which gives you the identity, is k. And if 2 is less than k, this is not the identity. And for problem 10, there's several parts, but they're all basically the same. Suppose you have a function f from g to g defined by f sub a. F sub a of x is a times x. A is an element of g. So if f sub a of x equals f sub a of y, that means that ax equals ay, which means a inverse ax equals a inverse ay. You multiply, and the a's cancel, so x equals y. So therefore, f sub a is 1-to-1, or an injection. And let y be any elements of the group, let x be equal to a inverse y, which is in the group. Then f sub a of x is ax, but x is a inverse y. So that's a inverse times y, which is e times y, which is y. So in my group, I have a y, and I just found an x that goes to y. So therefore, f sub a is onto, or surjective. And what it means for a function to be a bijection is that it's 1-to-1 and onto. So f sub a is a bijection, or same thing, 1-to-1 and onto. Any questions about any of these, or anything that I need to explain more? Okay, so let's go on to more algebra. So what will be the next chapter in the notes, and I'll post a lot of it this afternoon, is the additive group Z of integers. Which is an abelian group, plus 2 plus 5 equals 5 plus 2. So we've studied in some detail two non-abelian groups, the matrices, 2 by 2 matrices under multiplication, and permutations under composition of functions. What in a certain sense is an easier group is just the ordinary group of integers. And what are the properties of addition that you know without thinking that you know them? Associativity, right? If you have any three integers, x plus y plus z is x plus y plus z, right? 2 plus 7 plus 3 is the same as 2 plus 7 plus 3 plus 9 plus 3 equals 2 plus 10. Right? You have an identity element, which is 0, right? X plus 0 and 0 plus x is equal to x for all x. Right? 3 plus 0 and 0 plus 3 equals 3. And we have an inverse. For all x, there is a y, these are all integers, with x plus y equal y plus x equals 0. For example, 3 plus minus 3 and minus 3 plus 3 is 0. And we write minus x for the additive inverse of x. And we could also, if you like, define subtraction. Right? The binary operation is addition. We define subtraction, x minus y, as meaning x plus the element minus y. And then the fourth property is addition is commutative. X plus y equals y plus x for all x. Right? 2 plus 7 equals 7 plus 2. So under addition, Z is an additive abelian group. But you're not required to forget what you learned in elementary school, which is we can also multiply integers. And multiplication has the following properties. It's associative. xy times z is x times yz. So for example, 2 times 3 times 7 is the same as 2 times 3 times 7. Or 6 times 7 is 2 times 21. Right? There's an identity. It's the number 1. X times 1 and 1 times x equals x for all x. 1 times 3, 3 times 1 is 3. We have distributivity. If you have x times y plus z, that's xy plus xz. So for example, 2 times 3 plus 7 is 2 times 3 plus 2 times 7. This is 2 times 10, which is 20, equals 6 plus 14, which is also 20. And we have commutativity, xy equals yx for all x and y. 2 times 3 equals 3 times 2. And we have also a property I'll call cancellation. If x is different from 0 and xy equals xz, then y equals z. Okay. You can't divide one integer by another because the quotient not necessarily an integer. You can't divide 7 by 3 and get another integer, but you do have this cancellation property, which is very good. And in the notes, I prove this, but you learned this in elementary school and without a proof. We have what is called the division algorithm. So we have integers a and d, with d positive. There exist unique. So this is two statements, existence and uniqueness. There exist unique integers q and r such that a is dq plus r and r is between 0 and d minus 1. So this is just long division. This is says you can take a and divide it by a positive number d. Q is the quotient. R is the remainder. So if you take, for example, a equal to 76 and d equal 9, let's see, what did you do in elementary school? You divide 9 into 76, that goes 8 times and leaves a remainder of 4. So 76 is 9 times the quotient, 8, plus the remainder of 4. That's the Q, the quotient. This is the remainder. So this is, if you like, just giving a name to what you learned in, a long time ago. Division. Division is always possible. You can always divide by a positive number. You can even divide by a negative number and still get a positive remainder, but I don't need to do that. Any questions about this? Okay, now, a very basic notion in algebra, and in particular in number theory, is divisibility. So the integer d divides the integer n if n is dq for some integer q. And when this happens, d is called a divisor of n. N is a multiple of d. Q is the quotient. And sometimes another word for a divisor is a factor of n. Okay. So for example, 7 is a divisor of 1001 because 1001 is 7 times something. 7 times what? Well, if you divide 7 into 1001, it divides evenly. 7 times 143. Okay. 9 is not a divisor of 1001, because if you divide 9 into 1001, you get a remainder of 2. By the division algorithm, 1001 is 9 times 111 plus 2. So this remainder r is not 0. So you can also say that d is a divisor of n if the remainder, when you use the division algorithm, is 0. Okay. Again, there's nothing here that you haven't learned a long time ago. And what is often an interesting question in algebra and number theory and many other cases is we say that d is a common divisor of integers a and b if d divides a and d divides b. For example, 3 is a common divisor of 741 and 282. Why is that? Well, let's see. If you divide 3 into 741, three divides evenly, no remainder. 3 into 282 also divides. 741 is 3 times 247. 282 is 3 times 94. So 3 is a common divisor. Two is not a common divisor. Two divides 282, which is 2 times 141, but 2 does not divide 741. And there is the following problem. In general, compute the greatest common divisor of integers a and b. Just to make it a little bit simpler, let's say positive integers. And it's very common, for example, when you're taking a beginning class in computer programming, to have to write a computer program that solves this problem. You input the numbers a and b, press enter, and your program spits out the greatest common divisor. And the very close to the best computer program for doing this was discovered before there wasn't even a concept of a computer. It's in Euclid. There's something called Euclid's algorithm, or the Euclidean algorithm, to calculate the greatest common divisor of two integers. And it is remarkably efficient computationally. And here's what it is. So we have positive integers. Just to make it simple, let's make sure we just write them as so. Suppose that b is less than or equal to a. Divide a by b using the division algorithm. So a is b times some quotient plus a remainder. I'll call this Q1 and R1. And sometimes, just for simplicity, suppose we let D0 be A and D1 be B. This is just a notational device. So then this becomes D0 is D1 times Q1 plus R1. And actually, what I want to do, if I'm going to follow my notes, is call the remainder D2. So this is just changing the notation to make it easier to follow. So this is A, this is B. Take A divided by B, call the quotient Q1 and call the remainder D2. If D2 is not, so if D2 is 0, then D0 is D1 Q1, which means A is B times Q1, which means B divides A, and B certainly divides B. And so the greatest common divisor GCD of A and B means the greatest common divisor of A and B. The GCD of A and B is B, right? I mean, if this is 0, B divides A and B divides itself, then nothing bigger than B can divide B. If D2 is not 0, then of course, what do we know? The remainder is always less than what you're dividing by. All right. Let me just say, the remainder is always strictly less than what you're dividing by. Now take D1 and divide it by D2. So take D1, that's D2 times some quotient, Q2, plus the remainder. And this remainder, again, is smaller than what we're dividing by and greater than or equal to 0. And if D3 is 0, then what do we have? We have the following equations. D0 is D1 Q1 plus D2. D1 is D2 times Q2. So if you look at this, what does this say? It says D2 divides D1. And if D2 divides D1, this is divisible by D2, plus this, which is divisible by D2. These are two multiples of D2. D2 divides D0. So D2 is a common divisor of D1 and D0. And if some number divided both D0 and D1, then it would also divide D2. So any common divisor is in most D2, and we've just calculated the greatest common divisor. So this is the idea of the Euclidean algorithm. So to compute the greatest common divisor of A and B, take A, divide it by B, and you get a remainder, I'll call it D2. Take B, divide it by D2, and you get a remainder D3. Now, D2 is less than B and greater than or equal to 0. D3 is less than what you're dividing by and greater than or equal to 0. Take D2, if D3 is not 0, divide D2 by D3. And you get a remainder D4. And D4 is less than D3, which is less than D2, which is less than B, which I call D1 sometimes. And keep doing this. Like, take, if D4 is not 0, divide D3 by D4, and you get a remainder D5. And continue. Now, the important thing is to look at what happens as your remainders. D2, D3, D4, this is a strictly decreasing sequence of integers. The remainders satisfy, this is a strictly decreasing sequence of non-negative integers. This cannot go on forever. if you have a strictly decreasing sequence of non-negative integers, it has to be finite. There are only finitely many numbers, integers between 0 and b. And it stops when you get a remainder. Let me see what notation I used in the notes that I'm going to send out. D sub k plus 1 equal to 0. So I continue, and I will finally get d sub k minus 1 is dk qk plus 0. Let me write this out on the next page so I have a little bit more space to show you what's going on. So I want to find the greatest common divisor of A and B. So I have A, which I'll call D0. I'll divide it by B and get a quotient plus a remainder. And I can call this D0 and this D1 just so I have this notation. D0 is D1Q1 plus D2, but again, this is A and this is B. And I continue this process, divide D1 by D2, I get a quotient plus a remainder. I get D sub k minus 2 is D sub k minus 1, Q sub k minus 1, plus a remainder D sub k. And D sub k minus 1, when I divide by D sub k, I get a remainder of 0. And I have to get a remainder of 0 at some point because D1 is bigger than D2 is bigger than D3. These remainders are a strictly decreasing sequence of positive integer of non-negative integers. So it has to terminate. And I claim that D sub k is the greatest common divisor of A and B. D sub k is the last positive remainder. So let me do an example. I'll take an example that will be in the notes. So you can see numerically, certainly, what's going on. So this is an example. Suppose I let A be equal to 12,825 and B equal to 4,095. So of course you can tell by looking that both of these numbers is divisible by 5. So 5 is a common denominator of A and B, but it might not be the greatest common divisor. So we do division. 12,825, if you divide by 4,095, you get a quotient of 3 and a remainder of 540. Then you divide 4,095 by 540, you get a quotient of 7 and a remainder of 315. Then you divide 540 by the remainder, 315, you get a quotient of 1 and a remainder of 225. And 315, when you divide by 225, gives a quotient of 1 and a remainder of 90. And 225, when you divide by 90, you get 2, that's 180 plus 45. And when you divide 90 by 45, you get a quotient of 2 and a remainder of 0. So the last positive remainder is 45. And notice these remainders are strictly decreasing. 540, 315, 225, 90, 45. So the GCD of 12, 825 and 40, 95 is 45. And if you look at this and work your way backwards, you can see that 45 is a common divisor. 45 divides 90. So 45, so if this is divisible by 45 and this is divisible by 45, so is 225. If 90 and 225 are divisible by 45, so is 315. If 225 and 315 are divisible by 45, so is this. So these are divisible by 45, so this is this. So just working backwards, we can see that 45 divides both of these numbers. And if something D divides these two numbers, it divides this. And if it divides this and this, and it divides this, you just work your way backwards. And you see that every common divisor of 12, 825 and 40, 95 divides 45. So the greatest really is 45. So you really need to work a lot of numerical examples to really understand what's going on. We can also do the following thing, which is also a consequence of the Euclidean algorithm. Let me save this where you can see it. Let's work backwards. According to this, the greatest common divisor of 12, 825 and 40, 95 is 45. And 45 is this minus this. It's equal to 225 minus 90 times 2. But according to this, 90 is 315 minus 225 times 2. What is this? This is 225 plus another 2 times 25. This is 225 times 3 minus 315. And according to this, 225 is 540 minus 315 times 3, which is 540 times 3. And I have, oops, sorry. 225 is 540 minus 315 minus 315. This is equal to 540 times 3 minus 3 times 315 minus 315. That's minus 315 times 4. And 315 and 315 is 4095 minus 540 times 7. So let's see, what do I have here? I have 3 times 540. I have 28 times 540. 3 plus 28. I have 540 times 31. Oops. times. Let's see, I think I did something wrong. I have 225 times 3 minus 45 is 225 minus 90 times 2, which is 225 minus, and 90 is 315 minus 225. So that's 225 times 3, and I have minus 315 times 2, minus 315 times 2. Okay. And then this is 540 minus 315 times 3, minus 315 times 2. So here I have 3 times 315 and 2 times 315. That's 5 times 315. So this is a 5 here. So now I have 3 times 540, 35 times 540. So that's 38 times 540 minus 4095 times 5. And 540.
Professor, when did 2 switch to 5 again? Is it 2 times 315 or 5 times 315?
You're looking here?
Yes.
So here I have 2 times 315, and here I have 3 times 315, and 2 plus 3 is 5.
Okay, thank you.
Right? And my 540 is 12 825 minus 4095 times 3. So multiplying that times 38 minus 4095 times 5. So let's see. I have 540 times 38 minus 4095 times 5, but 540 is 12 825 minus 3 times 4095. So that's 12 825 times 38. And here I have 3 times 28 is 84, and 5 is 89. Let's see. All I'm doing is arithmetic. There's nothing intellectually difficult here. It's just managing to get the arithmetic to be correct. 38 times 12,825. Oh, and 3 times, this is a 3. And 3 times 38 is 114, and 5 is 119. Good. That's it. So the point of this calculation is that not only is the greatest common divisor of these two numbers equal to 45, but you can write 45 as a linear combination of the two numbers, 12,825 and 4095. You can always work your way back from the Euclidean algorithm to find an explicit expression of the greatest common divisor as a linear combination of the two numbers you started with. So again, there's only one way to understand what's going on, and that's to just work a lot of examples. Let me just show you one other interesting thing you can do with the division algorithm. And so let me go back. Here's my division algorithm applied to these two numbers. So if I take 12, 825, and I divide by 4095, I get 3 plus 540 over 4095, right? Just divide by 4095, this is what you get. Let me do the following sort of strange thing. This is 3 plus 1 over 4095 over 540. So this is 3 plus 1 over, and 4095 over 540 is 7 plus 315 over 540, which is 3 plus 1 over 7 plus 1 over 540 over 315. And 540 over 315, 540 over 315 is 1 plus 225 over 315. So this is 3 plus 1 over 7 plus 1 over 1 plus 1 over 315 over 225, which is 3 plus 1 over 7 plus 1 over 1 plus 1 over 315 over 225 is 1 plus 90 over 225. And this is 3 plus 1 over 7 plus 1 over 1 plus 1 over 1 plus 1 over 225 over 90. And 225 over 90 so 7 plus 1 over 1 plus 1 over 1 plus 1 over, sorry, 225 over 90. 225 over 90 is 2 plus 45 over 90. Plus 1 over 2 plus 45 over 90. So this is 3 plus 1 over 7 plus 1 over 1 plus 1 over 1 plus 1 over 2 plus 45 over 90 is 1 over 2. So we have this interesting expression for my fraction. 12,825 over 4095. It's what's called a continued fraction. So it's this compound fraction with ones in all of these numerators. 1, 1, 1, 1, 1. And I have the number 3, 7, 1, 1, 2, 2. If you go back to the division algorithm, 3, 7, 1, 1, 2, 2, these were the successive quotients in the division algorithm. So this division algorithm and the Euclidean algorithm, pretty interesting. So sometimes people say, well, you know, it's so hard to prove things in algebra. Aren't there some numerical examples we can calculate? And if you want some calculations, some numbers, there aren't a lot of numbers necessarily in mathematics, but computing the greatest common divisor of two numbers by the Euclidean algorithm, writing the greatest common divisor as a linear combination of the numbers a and b, and expressing a over b as a continued fraction, it's all calculational. It's all kind of interesting. Okay, well, any questions about this? Maybe I'll do one more example just for fun. Suppose I take some smaller numbers. And suppose I take a equal to 91 and b equal to 49. So I want to compute the greatest common divisor of 91 and 49. And I want to, let's call this number, whatever we'll call it, d, and compute x and y such that d is 91x plus 49y. So we take 91 divided by 49, we get a quotient of 1, and a remainder of 42. Take 49 divided by 42, you get a quotient of 1 and a remainder of 7. Take 42 divided by 7, you get a quotient of 6 and a remainder of 0. So the GCD of 91 and 49 is the last positive remainder, which is 7. And 7 is 49 minus 42. And 42 is 91 minus 49. So this is 49 times 2 minus 91, or if you like in this form, this is 91 times minus 1 plus 42 times 2. Oops, let's see, something's not right. Plus 49 times 2, that's correct. So x is equal to minus 1 and y is equal to 2. And if you wanted to calculate the continued fraction, 91 over 49 is 1 plus 42 over 49, which is 1 plus 1 over 49 over 42, which is 1 plus 1 over 49 over 42 is 1 plus 7 over 49 is 1 plus 1 over 1 plus 1 over 7. So that's the continued fraction. Any questions about this? Okay. Questions about anything else? Well, that's a good chunk of material. So I think we will quit for the morning and be back on Wednesday. Okay.
All right. Have a nice day.
Thank you. You too.
Thank you, Professor.